The biggest machine in the world is going to restart after 3 years of shutdown and upgrades. The Large Hadron Collider is the world's largest and highest energy particle collider. It consists of a 27-kilometer-long ring of superconducting magnets where energetic particles smash into each other, leading to spectacular collisions and discoveries. The LHC ran its first collisions in 2010 at an energy of 3.5 tera-electron-volts. Over the years, LHC has made some spectacular contributions to particle physics. It changed our understanding of the universe with the discovery of the Higgs boson in 2012 and paved the way for the discovery of more than 50 new particles. However, at the end of 2018, LHC was shut down for 2 years for further upgrades. Although the shutdown was planned for only 2 years, the ongoing pandemic delayed operations longer than expected. So what can we expect in the upcoming operations of the LHC? How will the biggest particle accelerator shape the future of particle physics? And most importantly, what will be this machine's most important scientific goals? The current perception of the universe relies on understanding the standard model of particle physics. Developed gradually throughout the latter half of the 20th century, it's a theory that beautifully describes electromagnetic, weak and strong interactions. But it does not include any description of gravity. Neither it explains dark matter and dark energy that make up 96% of the observable universe. So although the standard model has stood several tests in time, it is still not an accurate description of the universe. Moreover, 2021 was a big year in the realm of particle physics. Physicists have been looking for a fifth force for decades, and last year, they observed something in support of this. According to the standard model, a beauty quark should not discriminate between an electron and a muon while decaying. A muon is a carbon copy of an electron, except it is 200 times heavier. So the rate at which the beauty quark decays into a muon must be equal to the electron. But in March 2021, the researchers found that the muon decay was only happening about 85% as often as the electron decay. Nature seemed to be preferring one decay channel over the other, which is a violation of the law of lepton universality, according to which all three types of charged lepton particles, electron, muon, and tau, should interact in the same way with other particles. This indicated the presence of a fifth fundamental force, or a completely new exchange particle. However, the energy limitations of LHC couldn't provide much reasoning behind this speculation. But now, the upgrades have boosted the power of the Large Hadron Collider to another level. Now it can carry out collisions at 14 TeV, which is higher than the existing limits. This means that the batches of tiny protons traveling in beams around the circular accelerator together now carry the same amount of energy as carried as a 360,000 kilogram passenger train traveling at 160 kilometers per hour. This will allow physicists to discover new particles that were too heavy to see at lower energies, and eventually help unfold the mysteries beyond the standard model. In addition to this, the new upgrades will also allow physicists to shed some light on the hierarchy problem. The hierarchy problem deals with the large discrepancy between the aspects of the weak force and gravity. It basically asks why the weak force is 10 raised to power 24 times as strong as gravity. More technically, it ponders the discrepancy in the mass of the Higgs boson and those of other fundamental particles. So the upgrades will allow performing experiments that can provide insights into how the Higgs boson decays, and how this can prove to be an essential step in understanding how it fits into the standard model. LHC has a total of 8 detectors designed for different purposes. while the ATLAS experiment and the compact muon solenoid (CMS) are large general-purpose particle detectors. ALICE and LHC-B have more specialized roles in understanding the interaction of matter. And the last four detectors, TOTEM, MOEDL, LHCF, and PHASER, are much smaller and kept for very specialized research. During the maintenance, even these detectors receive major changes. Following this, LHC aims to conduct experiments targeting dark energy and dark matter, which are the most unexplained companions making up most of the universe. Unlike normal matter, dark matter does not interact with the electromagnetic force and absorb, reflect, or emit light. Many theories also claim that the dark matter particles would be light enough to be produced at the LHC. And even if they were created at the LHC, they would escape through the detectors unnoticed. However, there lies a silver lining. Even if these particles are extremely lightweight, they would still carry away energy and momentum with them. So physicists can infer their existence from the amount of energy and momentum that goes missing after a collision. And with the improvements that have taken place in the detectors, the new experiments at the LHC may now be able to provide more direct clues about dark matter. In the coming years, LHC is going to get even more upgrades. There are already plans to narrow down the LHC's beams and drastically increase the number of collisions after the 2024 maintenance session. The upgrades will allow LHC to see between 120 to 250 collisions every time a pulse of protons passes each other. Then, even the accelerator's name will be changed to High Luminosity Large Hadron Collider. Furthermore, all the detectors will also be upgraded to handle the increased luminosity at the number of simultaneous particle interactions. This version of the LHC is expected to begin experiments in 2028. The LHC is on its way to changing our basic understanding of our universe, and with this, we wish it a great restart. If you're interested in studying astrophysics at home, make sure to check out our Basics of Astrophysics series, the link to which is given in the description. This series explains everything at the most fundamental level, from the EM spectrum to telescopes, and from the birth of stars to the formation of black holes and galaxies.